Okay, so welcome back. We're going to go over the second topic, which is implicit differentiation. And so why do we care about implicit differentiation? What is implicit differentiation used for? Well, a graph is not always given by y as a function of x. Sometimes it's given implicitly by f of x comma y is equal to a constant. And its solution can be graphed in the xy plane, a set of points x comma y that satisfy this equation. Here's an example. We can graph this equation, x squared plus xy squared plus y to the fifth is equal to 3, plotting all these points that satisfy this equation in the xy plane. Notice this actually does not define y as a function of x because it does not pass the vertical line test. And even if you just look at a piece, say around 0.11, you still will not be able to solve for y as a function of x. Y is a function of x around there, but you cannot solve for y as a function of x in closed form, meaning there's no nice formula for it. And if there's no nice formula for it, how are we going to differentiate? Well, it turns out we can still differentiate using a technique of implicit differentiation. That's the power. The function might not have a nice form, but we can still differentiate. So let's say we want to determine the equation, the tangent line of this curve at the point 1, 1. We use a technique called implicit differentiation. Here's how it works. We start with the function f of x comma y is equal to a constant. We differentiate both sides with respect to x. And you apply the product, quotient, and chain rules where appropriate. Here we're treating y as an unknown function of x. And remember, when you apply the chain rule to, or generalized power rule to y as a function, to y as an unknown function of x, and to this function, y, the unknown function of x to the r power, you get this, r times y to the r minus 1 times y prime. That's because r comes down by the generalized power rule or chain rule. The power function, something x to the r power, that is the outside function, y is the inside function, r comes down, r times y to the r minus 1 times y prime. And so when we're multiplying by y prime, we're multiplying by the derivative of the inside function, derivative of this function y. Collect like terms and solve for y prime in terms of x and y. That's the second step. So when you differentiate both sides of this with respect to x, you're going to get a new equation that's going to look like the derivative of the right-hand side is always going to be 0 because the derivative of the constant is always 0. And when you, the terms on the left-hand side, some terms are going to have factors of y prime, some terms are not. You collect like terms, you collect in particular the terms that have a factor of y prime in them, and then you solve for y prime as a function of x and y. And then, especially if you're trying to find the equation of tangent line, you plug in the given values of x and y. In this case, x is equal to 1, y is equal to 1. Here's a problem. Here's an example problem. Find the equation of tangent line of the curve x squared plus xy squared plus y to the fifth is 3 at the point 1, 1. First step, differentiate both sides. X squared plus y squared plus 2x y times y prime plus 5y to the fourth times y prime is 0. Collect like terms. So notice we collect all the terms that have a factor of y prime in them. It's important to remember here when we differentiate this, right? Derivative of x squared is 2x. Derivative of xy squared, that's a product of two functions, x and y squared. Its derivative is the derivative of the first factor. Derivative of x is 1 times the second factor plus the first factor, x, times the derivative of the second factor, x times 2y times y prime. By commutativity of multiplication, you get 2xy times y prime. Here, derivative of y to the fifth, we've seen this before, by generalized power rule is 5, y to the fourth times y prime. And when we collect these terms, we collect all the terms here that have a factor of y prime in them. We get 2xy plus 5y to the fourth times y prime is equal to 0. We solve for y prime to get this formula, 2x plus y squared over 2xy plus 5y to the fourth. And finally, step 3, we plug in the given values of x and y. X is 1, y is 1, so we get this formula, negative 2 times 1 times plus 1 squared over 2 times 1 times 1 plus 5 times 1 to the fourth. So we get minus 3 over 7. 2 plus 1 is 3. 2 plus 5 is 7. Y prime, so we have slope of the tangent line y prime, which we found to be negative 3/7. We also have the point the tangent line passes through. A line is specified by a point and a slope, in this case negative 3/7 and 1, 1. And we can plug this into the point slope formula to get the equation of the tangent line. Y minus 1 is negative 3/7 times x minus 1. We can solve for y just by distributing negative 3/7 to both terms to get negative 3/7 x plus negative 1 times minus 3/7, which is 3 over 7, plus 1, that's 3 over 7 plus 7 over 7, 10/7. We get negative 3/7 x plus 10 over 7. And here's a graph of what's going on. Here's our curve. The red curve is just the curve that was given to us, x squared plus xy squared plus y to the fifth is 3. And the green line is the tangent line to this curve at the point 1, 1. Okay, so that's how implicit differentiation works. I will see you all on Monday.